I think so. Hello, Claire and Julia. Two of you are not here today. However, look who's here. Hannah and Julia are here. So, and me. And so 50%. We just prayed, and now we're going to talk. I'm going to lecture the last part of chapter 11. I think that's going to have to do. Hope that works, you two. Bernoulli, B-E-R-N-O-U-L-L-I. I think is how you spell his name. Let me look at the camera and see if, I think you can read that. Bernoulli's equation is what we still have to talk about. Now it's about pressure and things that change the pressure of a fluid. Pressure. Here's some things you already know about pressure. You know it's equal to F over A. You know the pressure of a fluid could be equal to PO plus rho GH, where the H is how far down you go in the fluid. The deeper you go, the more the pressure is, like if you're underwater. So we've talked about those equations before. Bernoulli's equation puts all of the factors into one equation that includes everything that really matters with pressure in a fluid. So the things that matter, really there are two things that matter, and one of them is, you already know, it's the H, how far down you are. The farther down you go, the more the pressure. The higher up you go, the less the pressure. That's the H. Like if you're way down at the bottom of the swimming pool, you feel a lot of pressure. As you come up, you feel less pressure. So H is part of it. And we know that is what makes a difference there. So one of the factors is rho, that's density, rho GH. The other one, though, that we haven't talked about is how fast the fluid's moving. Now, we talked about it a little bit. We had this equation, AV equals AV, which is the equation of continuity, which basically says the flow rate has to be the same at two different parts of a pipe. Even if you change the thickness of the pipe, that's the cross-sectional area, that would change the speed of the fluid. If you make it a bigger, fatter pipe, it's going to be less velocity. Increase this, decrease that. So we've talked about that. We've talked about velocity that way, but we haven't related that to pressure until now. Here's the thing about pressure and velocity. If air, let's let the fluid be air. If air is like wind, air is flowing with a great velocity past something, do you think that increases or decreases the amount of pressure on that surface? What would you guess? What? I didn't hear what you said. Increase. It would increase. If it's going faster, it'd be more pressure?
Yes.
Julia, come in. It's dark because we're recording. Hey, Claire, Julia Z just got here. What, you don't believe me? There she is.
Hey.
There you go. We were recording it for the two of you, but now we're just recording it for Claire. All right. Claire's sick, according to an email she sent me, but she misspelled the word sick. You know how Claire likes to misspell things.
Did she spell it with two C's?
Yeah. Is that
That's
a
not even
thing?
a thing.
That's not?
Like, not with the word sick.
Well, you would expect Claire to not do it if it's a thing. That's just Claire. Do you all know Claire? Do you know Claire Eakes? I'm just kidding. Okay. We're just kidding, Claire. We love you with all our hearts. I'm trying to get the camera set here, Claire. Maybe that's all right. All right, so we're talking about velocity, but I'm sorry, Julie, it's the opposite. The faster the fluid moves, the less pressure there is. Now, that may not sound intuitive to you, but it is. Let me give you an example. Let me give you an example with two sheets of paper. All right, Julia, come up here. Now, Julia is going to hold these two sheets vertically like this, yeah. And then just hold them like this, so get them in front of you. And then she's going to blow out of her mouth between the two sheets so that, oh, I'm sorry. So air is going with great velocity between the sheets, but not on the outside. Now, if what I said was true, what should happen?
Close it.
They would actually come closer together because if you increase the velocity, you decrease the pressure between them. Now, if that doesn't happen, you would just expect the air you blew down there to blow them apart. And that might be what you would guess. So we're going to let Julia blow down and see what happens. Go ahead. See how they came together?
You want me to keep doing it?
That was good. You want to do it again? Feel free. Yeah.
Wait, I gotta get them apart.
See how they come together, whereas you might think that was good.
Thanks.
If that wasn't the case, then just the air itself you're blowing down there, you might think would blow them farther apart, but it doesn't. It actually pulls them together, and the reason is increased velocity is decreasing pressure. So there's less pressure between them, that's what pulls them together. All right, so I'm showing you that really is true, this thing I'm telling you about velocity. So let me actually come now to the equation P for pressure plus the velocity part is not just V, it's 1/2 rho V squared. By the way, when you read this section tonight and take notes, they'll show you how this equation was derived. We're not going to take time in class to show you why it is 1/2 rho V squared. But when you look at that, you kind of think of energy, don't you? It looks almost like 1/2 mv squared, doesn't it?
It does.
And indeed, this whole equation, I'm not through with yet, is a conservation of energy equation. That's what it's about. All right, so here's where the V is. So there's another part which is rho GH, but instead of H, in this equation, for some reason, we use a Y. It's the same idea. It's how it's vertically in the fluid, how deep are you, or how high. Actually, Y is how high you are above the bottom. So it's a little different. When we used H in this equation, H was measured from the top of the surface of the water down to wherever you are. It was that, where that was a positive number, whereas Y would be measured from the bottom up. Okay, so here's the idea, and that's the left side of the equation. But what I can say is that's a constant, and rather than writing more stuff on the right side of the equation, that's a constant, which means these three things affect each other. The pressure of the air, let's just, as an example, use air as the fluid. The pressure of the air, then this is 1/2 density of air times the speed of the air, if the air's flowing like wind. And this is density times 9.8 times Y, how high up you are in the air. So here's the idea. We just saw if you increase the velocity, as Julia was blowing the air between the sheets, if you increase the velocity, everything here has to remain the same. That is, when you add these three things together, you get the same thing. So if you increase V, it's got to decrease something, and that's the pressure, because we didn't change the height. So if you increase velocity, it has to decrease pressure, so these three things will still add up to a constant. Now the same would be true if we went up higher in the atmosphere. That's Y. If you go up higher, that's increasing Y, that would have to decrease pressure. And so this equation explains why when you go up in the atmosphere, the air pressure is less. It just explains that it is. Let's say the wind is not blowing at all, so the V doesn't change as you rise. You're in a hot air balloon and you just go up. Well, the wind doesn't change, so this doesn't change at all, but as you increase Y, you're getting higher, it would decrease the P. So when you add these three things together, it's still a constant. See how this works?
The same constant or a constant?
No, it's just the same for that particular air. Now, often I write the equation like this, where that's P1, and that's V1, and that's Y1, and over here is P2, plus rho, 1/2 rho, sorry, 1/2 rho, am I still on the camera? No, I'm about to go off the camera. Rho V squared, but that's 2 plus rho G Y2. So this is really all of Bernoulli's equation. If you were actually plugging in numbers, you would think of it that way. Where all these ones on the left side of the equation are at one position, and all the twos are at another position. But all of these on the left have to add up to the same thing as all these on the right. That's Bernoulli's equation. All right, I'm going to give you some more examples. We're not actually going to work a math problem, but I'm going to give you some more examples. Here, Claire, there's the whole equation. There you go. One equation was the 2 sheets of paper that Julia blew through, and you saw that when you increased velocity, it decreased pressure. All right, here's another one. Another one would be, here is a container, a large container of water that has a valve that opens up to the outside here. And so water can come out the bottom. You know what I'm talking about? Little container, a large container of water, 5-gallon tub of water, and you can open a valve here and out comes water. If the water, say, is way up here, the water level's up here at the top. Then there's a difference between here, position 1, and here, position 2, inside, just talking about inside the tub. This is much higher. So the pressure up here would be more or less than the pressure at position 2. What is it?
More. Less.
It'd be less. It's just like the swimming pool. When you get to the bottom, you feel more pressure. There's more pressure down here, less pressure up there. But here's why. When Y is a big number because you're up high, at position 1, you've got a lot of Y. Remember, Y is measured from the bottom up. So when Y is high, the P is low. So they'll add up to the same thing. Down here, the Y is 0, perhaps, at the bottom, so the pressure is more. Okay, so you can see that. Neither one is the water flowing here and here. It's just at rest. Even if you open the valve, it's not really flowing here and here. Okay, so that's not a factor, but this is. Now, let's talk about the water out here, though. Down here, the pressure is pretty high, we said, because of it's very small Y, so it's a lot of P. Down here, and if that was a swimming pool and you're at the bottom of it, you'd feel a lot of pressure at the bottom. So the pressure is high down here. However, out here, now I'm changing my problem to let this be position 1, and out here is position 2, out here. Well, we already know that the pressure is high at position 1, but the pressure is really low at position 2. In fact, the pressure at position 2 would probably be 1 atmosphere, because it's the same pressure. It's no longer got the weight of the water above it. It would be at the same pressure as the air around it, because what's above it now is just air. So if the air is 1 atmosphere pressure, then the water right here would be at 1 atmosphere pressure. So this is a whole lot less pressure than there. So if position 2 has less pressure, something else had to increase. Well, the Y didn't change. They're at the same Y. But the V changed, didn't it? Out here, the water's really flowing fast. It's coming out fast. So out here at position 2, you have a high velocity, so lower pressure. If one goes up, the other has to go down, so they'll add up to the same thing. Is this making sense?
Mm-hmm.
Okay. That's another example of Bernoulli's equation at work. Here's another example of Bernoulli's equation. An airplane. An airplane. Here's the airplane, and here comes the wing. No. Let's do it this way. you're looking at the cockpit of the plane, and there's the pilot right there. And so here, and then here's the wing. No, I don't want to draw it that way either. Let's get oriented. Here is, yeah, my first way was okay. Here's the airplane. All right, here's the airplane. Here's the cockpit up here, and here's the wing. The wing comes out and kind of does this, and it's shaped like that. Now the wing's coming out of the board. Can you see the wing there, Claire? And but it's curved. I kind of exaggerated the curve, but it is really just the wings of an airplane are curved like that, and then they're real skinny at the back end. Now here's what happens as the plane moves forward. The air, even if the air is not blowing, there's no wind, the air relative to the plane is going to be going this way. And it hits the front of the wing, and some of the air has to travel, some of the air travels that way below the wing, and some of it has to hit the wing and travel over like this. Now, the air that travels over the wing has farther to go. Can you just look at it and tell that? It has farther to go. If two molecules hit the very front of the wing and one of them goes below and the other goes above, the one that goes above is going to travel farther. And yet they have to get back to the back of the wing at the same time. That flow rate has to be the same. If they don't, then the air down here gets there faster and sooner, and the air up here hasn't gotten there yet. You create little pockets of vacuum and the whole thing shuts down. So that would never happen. What happens is the air is smart enough to know, I've got to get it back at the same time you do so that there can be a continuous flow rate. Well, that means the velocity is greater. Above here, at position 1, the velocity is greater than it is down here at position 2. It's greater up here. Well, if the velocity is greater, and the thickness of the wing is pretty much negligible. I mean, yeah, this is up higher than that, but it's not very much, not enough to matter. So if the velocity is greater, the pressure has to be what? Lower. So the pressure above the wing is less than the pressure, the air pressure below the wing. That's what gives the plane lift. That's why the plane goes up. It's Bernoulli's equation, yes.
So if it were to be like upside down.
If you put the wing upside down, it would never fly, yeah. Is that what you were going to say?
Yes, it's not always like the pressure is less on the one that's on top.
Not always. It has to be a greater distance to travel so that it travels faster. And the one that's traveling with a greater velocity, that side would have less pressure on it. If that's more, that's less, so they add up to the same thing. Yeah, that's the people who built first airplanes understood physics, because the whole idea of lift comes from Bernoulli's equation. Now there are other things. That's the airplane's not really that simple, but that's the big reason that the plane lifts up off the ground. That's the main reason the plane lifts up off the ground, is because there's greater air pressure below the wing than there is above it, pushing it up. Okay, airplanes work because of Bernoulli's equation. There's another example. You know what I wish I knew, Hannah? What time the bell rings on Tuesday? Anybody know? On first period, on Learning Lab Day?
First period, Learning Lab Day is 49.
49, we have till 49, okay. That's still 20 minutes. Still got 20 minutes, Claire. Here's another example. Here's a house. Here's a house. Okay, here's a door, here's a window, and this is the attic. Here is a tornado. You ever been in a house during a tornado? Julia, you have? Really? Really? Where were you?
I'm trying.
And there was a tornado nearby, somewhere not too far away.
It was windy.
It was really windy.
Windy.
Did the roof come off? Sometimes the roof will come off, and here's why though. People who don't know physics will say, well, the wind was so great from the tornado, it blew the roof off. But that's not really what happens. It's Bernoulli's equation. All right, so think about the air inside the attic. The air inside the attic pretty much has a velocity of 0, even though the wind's blowing outside, not inside. So the air inside the attic has a velocity of 0, but the air right above the roof has a very great velocity. See? Velocity. All right, and the difference in height is negligible right above the roof and right below the roof. So rho g y is not a factor, but where you have greater velocity, you would have what? Less pressure. So much less pressure above, very small pressure because the wind's really blowing fast, and much greater pressure. The pressure inside is still normal air pressure. And that's what pops the roof off. Is it that the wind from the outside just blew it off? It's the pressure inside becomes so much greater than the pressure outside that it pushes up and the roof comes off. Now once the roof comes off, the wind might blow it somewhere. But that pressure, that difference in pressure, Bernoulli's equation is what pops the roof off of a lot of houses during tornadoes.
So it like blows itself off.
Yeah, well, the pressure inside the attic is what blows it off. Yeah, it's not the wind. Now, the wind can do lots of damage and it can blow the roof into the next county and it can do other things, but it's the pressure in the attic that actually pushes the roof off. Yeah. All the great things you're learning. Bernoulli's equation explains a lot of things. One more I want to mention to you. If you kick a soccer ball, or you throw a baseball or a softball, or you could probably hit a volleyball, Julia. I don't know. But you hit it so that it spins. You ever hit a volleyball so that it spins? You do that on purpose?
Yes.
Okay. Let's say you hit this ball and relative to whatever way you're looking at it, it's spinning like that. And it's moving. It's moving toward the other side of the court, but it's spinning the way I've drawn it. Now, as it's moving this direction, the air is flowing back this way, right? The ball's moving to the right, so the air, which is not moving in the gym, it's just still air, relative to the ball, the air is moving this way. But the ball is spinning that way. So as the air comes in, some of it goes that way and some of it goes that way, but the air that goes this way is having to work against the spin of the ball, so it slows it down. So the way I've drawn the picture, the air underneath the ball is slower because the ball's spinning this way, but the air is flowing opposite. Above it, the ball's spinning the same direction the air is flowing, so that air would be faster. And if the air is faster, there is what? Less pressure. You increase the velocity, you decrease the pressure. This is what makes the ball curve. If you're a baseball pitcher and you're throwing a curveball, that's what you do. You spin it, and in the direction it spins, if it's spinning this way, there's less pressure here. The ball is going to actually curve that direction. This is a volleyball, or you can kick a soccer ball. I saw a girl kick a soccer ball from a corner kick one time, and it went this way and it just curved into the goal. We had a player on our team who did that one year. She scored on the corner kick, which is really hard to do because the goal's pretty much even with where you're kicking it. So you kick it this way and it has to curve in, and it did. And she scored because she gave it spin when she kicked it. Yes?
So like, in the event that it did not spin, did the air just like...
If it's not spinning, then the air is this way and the air this way should be about the same speed. If they have the same speed, they would have the same pressure. It shouldn't curve. If the ball's not spinning and there's no wind, it's just the air would be the same speed on both sides. So then it would just go straight. Okay. That's just another example of how Bernoulli's equation affects things. There are lots of examples. A sailboat uses Bernoulli's equation to line up the sail so that the wind's passing faster on one side than the other, and that makes the pressure greater on the side where it's going faster. So sailboats are not just let the wind hit it on one side and that pushes it. That will work, of course, but sometimes the wind's not blowing the direction you want to go. And the sailors who really know how to operate sailboats understand this. So they can set up their sail so that the wind's just going faster on one side than the other, and then that pushes it in a direction. There are just lots of examples of Bernoulli's equation that works. You can have curtains hanging at a window and open the window. Just open the window and the curtains are still hanging there. And if the wind's blowing it all outside, what would the curtains do? Would they be pulled toward the outside or pushed toward the inside or nothing? Yeah, they'd be pulled toward the outside because where the wind's blowing on the outside, there would be less pressure. Greater velocity, less pressure. Yeah.
My mom, like in the car, my mom's like a germ freak, so if someone coughs, like she'll just like crack the window.
Yeah, if you crack the window, there's a lot of speed outside but not inside, so there's the pressure of air on the inside because the pressure is greater would rush out. Yeah. In fact, that reminds me, you could be in a car. We're looking down at your car from the sky, and see here are your wheels, and you go in that direction, and here's the highway, and then this way, there's this great big massive truck. It's an 18-wheeler. And it's going that way. You don't have your windows. Your windows are all closed. That doesn't matter. As you drive this way, relative to your car, the wind's blowing back this way, right? Well, when the truck passes you, all of a sudden, the speed of the wind relative to you in the truck has increased because you're going opposite directions. And if there's an increase in the speed, there's a decrease in pressure. Your car feels like it gets sucked over toward that truck just for an instant while the truck's passing. Have you ever felt that? Great big vehicle going really fast, passes you going the opposite direction, and it feels like your car for an instant got pulled to the left toward that truck.
I heard one news that like a kid in China, he's is walking by a big truck and he got like into the
Oh, he got pulled toward the truck?
Yeah.
That's Bernoulli's equation, sadly. Sorry. Did he get hurt?
Yeah.
Oh, I'm sorry. Makes me sad. All right. Anyway, you can think of other examples as you go through your thoughts of how Bernoulli's equation works. All right, do I need to tell you anything else about Bernoulli's equation before we are through? Probably not. And that's the last thing in chapter 11 as far as teaching you new material. From chapter 11, the last thing was Bernoulli's equation. Last thing you need to know. So, I think we could take these last few minutes and go over some homework problem. Let's do that. To tell you the truth, I have no idea where we were last Friday when we were going over homework. So, can you all tell me where we were? Or what's the next one we need to work? I don't know. Let's see. I'm pretty sure we did we ever do the one about the log raft? We did that one, didn't we?
Yeah.
Okay, that was number 50, I think.
Yes.
Did we get past that?
Yes, we did numbers. Oh,
Did we do 56 and 7?
No.
We haven't done either of those. What, do you want to do those? Either one? Do we need to?
Let's take, who that answers number 56?
Oh yeah.
Yeah, 56, I have area of 9.3 times 10 to the 5th, I think, square meters. Was that the question, the area? Hope so. I've got that written down. That's 56. 9.3 times 10 to the negative 5th square meters. Any other even ones?
58.
58. 58. Did I give you 58? Ha, I did. Here it is. A is 0.042 meters per second. That's A. B is 0.38 meters per second. Yeah, that's 58. All right, do we need to do 56 or 58? 56, let's do 56. Anybody ready to read?
I can read.
All right, go ahead.
Okay, water flows straight down from an open faucet. The cross-sectional area of the faucet is 1.8 times 10 to the negative 4th square meters, and the speed of the water is 0.85 meters per second as it leaves the faucet. Ignoring air resistance, find the cross-sectional area of the water stream at a point 0.10 meters below the faucet.
We should do this. I just take a pitcher and pour water out, and you will. Here comes the water out of the. Here's a pitcher, and here comes the water, and it's like this when it first comes out, and as it falls, it gets narrower and narrower. Just look at it, and the reason is it's speeding up, and if you increase V, you decrease the area. See, AV equals AV. Just showing you. That's what this is about. All right, so AV equals AV is how you work this. The area is pi r squared. The pi's can actually cancel if you want them to. This first r was 1.8 times 10 to the negative 4th squared, because it's pi r squared, times v, and the v was 0.85, I think.
I have a question.
And then just do the same thing on the other side. Yes?
If 1.8 is the cross-sectional area, isn't that the diameter?
Oh, it was, wasn't it? So what we need is, was it the cross? No, it wasn't the cross-sectional area. What was that number? The radius or the diameter, Hannah? This 1.8. No.
The cross-sectional area of the faucet is 1.8 times 10.
Oh, so that was the area. We don't need pi r squared. Pi r squared is that then? Is that what we're saying? I think we are.
Oh, yeah.
So we didn't need to write it that way. This is the area and that's the velocity. Okay. So if that's true, then it's equal to the area times the velocity here, but we don't know the velocity here, so we have to find the velocity here. But the way to do that is our old friend Big 4. Because it's free fall, we know the acceleration is 9.8. That's A. And the initial velocity was 0.85. We're looking for the final velocity, but 0.85 squared is the initial velocity. The acceleration is 9.8. That was negative also. And we could just make them all positive if you'd rather, because even delta x, everything's negative. Just make everything positive. And 0.1. And when you solve that for final velocity, I get 1.64, I think. So you had to go back to the Big 4 to find the speed of the water when it's fallen 0.1 meters. And that's the V here. So it's now 1.64, and you can solve that for A, but then the question was, yeah, the question was A. So that, according to my math, that comes out to be 9.3 times 10 to the negative fifth. You would expect it to be less than this because it's as it gets faster, it gets skinnier. Because if you increase velocity, you decrease area. See? And it is. 10 to the negative 5 is less than 10 to the negative 4. All right, everybody see that? That was number 56, so we will try to remember to pick up from there. Tomorrow, I don't have any more lecturing to do now, so we have the whole period Wednesday and Thursday just to go over all the homework that you've been given. And the test is still Friday.
So after this, do we have just second period? There's not like learning lab?
Right, I think second period and then break and then learning lab.
Oh, do we have those, like, community groups?
Yeah, second period break and then learning lab after
Not
that.
today. I think it's tomorrow.
What did he say about learning lab today? Did he say anything?
There was student council meeting, but.
Okay. All right. Claire, thanks for being with us. Everybody say bye to Claire.
Bye, Claire.
Bye. We'll see you tomorrow. Hope you're well. Bye.